So far we talked about singular value decomposition. We saw that it gives us the best possible projection in terms of reconstruction error, but what we also saw is that there are two drawbacks. First drawback was computational, that it takes lots of time to compute. It kind of takes the cubic time in the size of the data to compute. And the second problem was that the results we get are these dense vectors that can take lots of space and are hard to interpret. So the CUR decomposition is a different type of dimensionality reduction technique. We will talk about it next. And basically, it tries to alleviate some of these drawbacks of singular value decomposition. So what is our goal? In general, our goal is very similar to the goal we had with singular value decomposition. So again, we are given matrix A, and we want to express it as a product of three matrices. Now these three matrices are called C, U, and R. And similar to what happens in SVD, our goal here will be that we want the difference between the original data and the reconstructed data to be as small as possible. While singular value decomposition gives us the optimality guarantee and says this is the best what we can do, here we will allow ourselves to maybe have a bit larger reconstruction error, but at a much smaller computational cost. And the way we will think about this is the following. We are thinking that we are given matrix A as an input. We want to express it as a product of three special matrices, C, U, and R. And as with singular value decomposition, we will put some constraints on the structure of matrices C and R. And the way we do these constraints is very interesting. So let's see how we are putting constraints on C and R. So the idea is the following. The constraint on our matrix C is that basically it has to contain columns from matrix A. So the way we will compose matrix C is that we will choose carefully, or using some algorithm, a set of columns from matrix A, and we will put those into matrix C. So our matrix C is simply a set of columns from A. Similarly, we will take the matrix R, and we will do the same, but now for rows. So what this means is we will pick a set of rows from matrix A and put them into R. So why do we call matrix R R? Because R stands for rows. And why do we call matrix C C? Because C stands for columns, right? So what are we doing so far is we will create matrix A as a product of three other matrices, where matrix C will simply contain columns from A, and matrix R will contain rows from A. And now, of course, the question will be, what is the matrix U? So the way we will compute the matrix U is that we will compute what is called the pseudo-inverse of the intersections of C and R. I will explain this in more detail, but that's basically the high-level idea. Why is this a good idea? Is because selecting rows and columns to fit them into C and R will be something that we can do very fast. And this means that the whole computation will be very quick and very easy to do. Okay, so the question is, how does CUR correspond to SVD, and is CUR decomposition doing anything useful for us? So first, let's assume the following case. Let's assume that A sub k is the best k approximation to our input matrix A. We already know how to compute A sub k. We compute it using the SVD, which means we take the matrix A, do the singular value decomposition, take the first k largest singular values, set the rest to 0, and multiply the three matrices together, and we obtain A sub k. And when I say best, right, we already know what best means. Best means in terms of the Frobenius norm, which means that A minus A sub k in terms of Frobenius norm is as small as possible. So now, what Mahoney and Drineas proved is the theorem that connects the quality of the CUR approximation to that of SVD approximation. And what the theorem says is that the reconstruction error of CUR is less than the reconstruction error of SVD plus some epsilon times the Frobenius norm of A. So basically, Frobenius norm of A tells us what is the magnitude of the values in matrix A. And what the whole theorem says is that the CUR reconstruction won't be too far away from the SVD reconstruction. It will be some additive error term away from the SVD reconstruction, which is kind of the best possible reconstruction we could achieve. What are the conditions for this to hold? So if we allowed SVD to pick k columns and k singular values, we will allow CUR decomposition to pick k times log 1 over delta divided by epsilon squared columns and k squared times log to the cube 1 over delta epsilon to the 6th rows, where I can think of epsilon to be something small, and I can also think delta as a small quantity. Of course, what is important to know here is that this is a probabilistic guarantee that says, you know, this equation up here, this guarantee will be true with probability of at least 1 minus delta. But what is important is that basically here we establish the quality of the CUR decomposition, but the computational time is much shorter, right? So the computational time to do this is of order m times n, which basically is the order of our data size, and that's much less than what we had for SVD, where we had it as m times n cubed. Okay? So what does this mean? This is kind of a complicated theorem, but what this means is that in practice we pick about 4k rows and columns, and we will do as well as SVD does when SVD picks k rows and columns. So CUR needs more of those, but there will be an important structure in real data which actually allows us to do much better with CUR than we can do with SVD.